Okay, so yeah, so Bohr said you have this positive nucleus because it was already proven, and then he said, but wait a second, this is wrong. The electrons aren't just stuck there, okay? They're moving around. So the electrons are on these levels, E minus, and he said that they're orbiting, but they're not doing that. So instead of kind of doing this, what they're kind of doing is this. Kind of randomly going wherever they want, but they're stuck on that level. So, I don't know, picture, I mean this school only has 2 levels, but, so, I don't know, picture a little kid running around the hallway randomly. I don't know, give them, what's the stupid stuff kids drink these days? Some sort of energy drink that's going to kill them eventually. So, give a kid a few energy drinks, throw a blindfold on them, let them run around the hall. That's what electrons do, okay? They're like little kids hopped up on sugar and caffeine and blindfolded, okay? They don't have any set path, that's the point. They run around, bouncing around all over the place. So it's kind of a random path. That's not a complete truth, I'm sort of lying to you. But if I explain really what happens, it's too confusing and I don't want to confuse you. So all that you really need to understand is this does not happen, okay? Why don't you put an X through that word orbit? That'll make you feel better. Yes, that's what he said, but it's not right. Okay, they do not orbit, but they are on levels, and that's important to understand that as you move down the periodic table, there's more levels, more electrons, atoms get bigger. Okay? Okay, so that was kind of the history of it. So well over about 2,200 years, long time frame, lots of different scientists. We're going to see this experiment today and that today. We're going to take notes on this, on this. He's got some things that he said we're going to take some notes on. But before we do that, the most current model, what do we call it? Wave mechanical model, right. So if you didn't get this down yesterday, make sure you get it down right now. Okay, so the most current model of the atom is the wave mechanical model, or sometimes it's called the quantum mechanical model. Quantum mechanical model. That's a QU. That's really messy. So yeah, quantum is a bundle of energy. Quantum, they're bundles of energy that electrons can gain or lose. We'll talk more about that. But really the big deal with a quantum mechanical model, it's also called the electron cloud model. So imagine a cloud. The cloud is the electrons, and then in the middle is this really hard, dense, positive nucleus. So electron cloud model is another way to say it. And the biggest thing with this is that the highest probability of finding an electron is in an orbital. So that's kind of the big deal with this, underline that word orbital. Kind of a big deal with the current model is that there are these little regions of space. Okay, this little, so I guess we can kind of, I'll erase this and write down what an orbital is. But an orbital is a little region of space that electron is confined to. And that's where you'll find an electron. So right now, you come into school, you're looking for a student, where would you look?
Always.
No.
In a student?
Right now, where would you find students?
No, front class.
In a classroom. The room is an orbital. This classroom is an orbital. If you guys are electrons, the best chance, you might find one in the hallway, but they're not supposed to be out there right now. There's a good chance you're going to find one in a classroom. Same thing with an atom. You want to find an electron, you got to go to the rooms. You got to go find the orbitals. Okay. So let me define what orbital means, and then we will move on. By the way, the people that get credit for this one, it's called Schrodinger and Heisenberg. Really smart, actually, physicists, not chemists, because when you get into advanced chemistry, it actually becomes more like physics. So this is a lot more physics than chemistry, actually. But anyways, an orbital, let's write down the definition, and then we're going to move on. An orbital is a region of space in an atom where electrons are located. And I abbreviate electrons E minus all the time, so hopefully you get used to that. E minus is electron. Okay, so now what we'll do, we'll take some notes on what Dalton said, then I'll show you the cathode ray tube, the example or experiment, then the gold foil, take some notes on it, and then explain table O a little bit further, and then we'll figure out how to find out the number of neutrons, and then we'll move on here. We got some worksheet. There's a worksheet I was going to have you do in class. We'll see if we have time. Okay, I know it's not super duper exciting, and it's a lot of me taking, writing notes and you listening, but stay with me. All right, here we go. So Dalton's theory. Dalton's atomic theory. 4 things. All elements are composed of atoms. So we already kind of wrote that. We'll write it again. All elements composed of atoms. And everything is made up of elements, so that means all matter is made of atoms, right? We talked about that. And we actually learned this early in the year. All atoms of the same element are identical. Same elements are identical. So if everybody in here was holding an atom of silver, everyone's atom would be identical. All atoms of the same element are identical. Atoms can be physically mixed. Or chemically combined. Again, this is kind of redundant. We've learned this stuff already, but again, giving the guy credit here, he kind of came up with this stuff, these ideas before even a lot of it was proven. And if we have a chemical reaction, so in chemical reactions, atoms can be, let's see, what do I have? How do I work this? Separated, joined, or rearranged. So they can be joined, separated, or rearranged. That's really all that you can do. You can take them, put them together, you can pull them apart, or you can rearrange them. So again, this is what Dalton's theories work. And just to help you understand how small atoms are, how many people on Earth? Anybody know?
7.
How many?
7.12 billion.
Yeah, about 7 billion people, right? Can we write that number? Can I erase this? Are we good? I can leave it up there. Fine. Let's write 7 billion out. Who can give me the number? What do I write? 7 and how many zeros? Tyler says 9. Is he right? That's how many people are on the planet. Is that a lot of people? Okay. Guess how many atoms, what do I have here as a number? How many atoms of copper there are on, if a penny was pure copper? Yeah, if a penny was pure copper, they're not. Old ones are. Before 1982, I think they are. Guess how many atoms are on a pure copper penny?
50 trillion.
50 trillion. How am I going to do this here?
It's going to be a lot here. Oops.
Yeah, no, that's right. That many.
What number is that? Wish I had that much blood.
I think it's 2.4 times 10 to the 21st. Right? 1, 2, 3. It's close enough. That's 7. How would we put this in scientific notation? 7.0 times 10 to the 9th. That's how many people on Earth. That's how many copper atoms are on 1 penny. So how many atoms are on this floor? It's a number I don't even understand how to write that number, right? It would be times 10 to the, and then that would be times 10 to the something. It would be absurd. So So atoms are ridiculously small. Not this atom. But most atoms that we're talking about in here are ridiculously small, okay? So again, that's how many people on a planet. That's a lot. That number dwarfs that number. So atoms are very, 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 very small. Okay. All right. So that's important to understand. All right. Now, let's write down Thomson's experiment and then Rutherford's. I'll show you the videos. We'll take notes on it. And then that might be it for today. All right. So the cathode ray tube experiment. Cathode ray experiments. This is how Thomson discovered the electron. I'll show you that first, then we'll do the gold foil. All right, lights please. Apparently I have an atom music video here. Probably pretty corny, but we might watch it. Not today, but all right. So, I gotta pull this thing. So here's some teacher somewhere, some school, I don't know, who has a cathode ray tube. I don't have one. If I had one, I would show you, but I don't have one. This thing here is producing a beam of electrons, and there's a piece of paper in there that's coated with this, like a chemical that shows up light. Probably has phosphors in it, is what it's called. But anyways, you can see the beam of electrons. It's a special kind of tube. So you have like an anode and a cathode here. Those are like terminals on a battery. Hook up electricity to it, and that essentially is a beam of electrons, which is basically what electricity is. So you see a beam of electrons. So long time ago, J.J. Thomson did a similar experiment. And actually, I think it was by mistake, he brought a magnet, or had a magnet on the table near this beam. And if electrons are negative and you bring a magnet towards it, what do you think is going to happen? It's either going to do one of two things, attract or repel. What does that prove? It proves that this beam has some sort of charge. And that's how they discovered the electron. They realized there's some charge here, there's something going on, and that led to more, discoveries of what it was. And it was a negatively charged electron. So I just want to show you how if you bring a magnet near it, the beam actually bends. And that was the cathode experiment for the electron.
This is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube.
So I don't know if that means anything to anybody, but there's nothing inside. That's the cool part about it. Electricity needs something to travel through. Okay? I can't remember that Tesla coil thing I had that I zapped the screws and the cork shot across the room. If I had that Tesla coil and I turned it on and just held it in the air, I couldn't point it at Ariel and zap her. Okay? Electricity can't go through the air. Okay? It doesn't work that way. Wait, doesn't lightning work that way? Yes, that's different. Okay? Lightning's a little different. But electricity needs something to travel through. And yes, there is actually air, right, in the room, and it technically can travel through the air. But the point is, in here, there's a vacuum. So the electricity can't just magically travel, but it does. And that was the cool part.
So he decided to apply a magnetic field to this cathode ray. And he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? It does appear as though it's happening to it.
So it's repelling it.
It's moving, it's being repelled, isn't it, by the magnet. When we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted
Okay,
there?
so it's just more of the same. So I just want you to literally see it because that's what this experiment was all about. He said he applied a magnetic field. I thought it was by mistake. Maybe I'm wrong. But anyways, the magnet will repel or attract the beam. While I have this hooked up, I'll show you the gold foil. Now let's do one at a time. Okay, you can keep the lights off here. Let's write this down. So all we need to write underneath cathode ray experiment is the beam of electrons was attracted to one pole or one end of the magnet and repelled by the other. And what did that prove? So that proved an electron has a negative charge. So that's it. All you need to know, I've seen this question one time on the Regents, but basically everybody got it wrong. And the reason, and I felt bad, is because I didn't stress it enough when I taught it. So all you need to remember is that cathode ray, electron. That's it. Connect those two in your brain. If you remember J.J. Thomson was part of it, I don't think they're going to ask that. I've never seen it. But I did see one time, it said, which of the following particles was discovered using the cathode ray tube experiment? And I almost died when I read it. I'm sitting there flipping through it, while you're taking the test, and I'm like, oh man. Some kids got it because I do teach it, I mention it, but I didn't really stress it. So now ever since then I stress it. So cathode ray, electron. Okay, next video. And we'll just go right to the bell. Don't forget that worksheet is due tomorrow. Gold foil experiment. So I'll show it now, we'll show it again tomorrow, and we're going to get chopped off by the bell here. But here's the gold foil experiment. Yeah. So it's very short. It's only 47 seconds, but I'm going to pause it and talk about it. All right, here we go. Stay with me. Don't pack up yet. Pay attention.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered.
Hold on. First of all, this is a radioactive source. What's that mean? Does anyone know what radiation is? It's radiation. Anyone have a microwave? Probably every single person in here has a microwave in their house. That uses radiation to cook your food. Or heat your food, not really cook it, but you can cook, I suppose. Microwaves, not the actual microwave, but microwaves going through the air. It's like these little waves that go through the air, are radiation. And you can use them to cook food or heat food up. Has anyone ever, you don't have to actually talk about it, it's kind of a personal thing, but if you ever known anybody who has cancer, had cancer, has cancer, family, friend, and they got treated with radioactive therapy, so radiation therapy. Has anyone ever heard of that at least? Yeah. Okay, yeah. My dad had cancer a long time ago, and he used to get radiation therapy, and it was like on his back, and his back would actually get warm from it. So I'm giving examples of what is it? It's these little particles or little waves that travel through the air that can heat things up, and it can actually kill cells. Anyways, this is a radioactive source. So in here, there's radiation coming out of it. So we'll talk a little bit more about that tomorrow. Don't forget that worksheet, front and back. Do tomorrow. I'll put the text out, I suppose. Someone hit the lights, please.